Okay, let's get started on our first column buckling example. We have an A36 steel column that is supporting a 50,000 pound load. The ends of the column can be modeled as pinned. It's 20 feet long and is made of a W6 by 15 beam. Our question is buckling a concern? So we're given that this is a steel column. In fact, we're given that it's A36 steel. We know this column supports a 50,000 pound load, and the length of this column is 20 feet. And we're told that the section is a W6 by 15 member. And we're asked to find, is buckling a concern? So let's get started with our solution. In our solution, we need several things. We need a mathematical model, some material properties, and geometric properties as well. For our mathematical model, we're going to use the one tool that we already have, Euler's Buckling. I'm going to call this equation 1 for Euler's Buckling theory equation, and I will define each of the different variables involved. Where P critical is the critical buckling load, which is a force, I'm going to use units pound force. I'll use E to be the modulus of elasticity of the column material, which is steel, in PSI. I is the moment of inertia of the section, and note this, around its buckling axis. We'll talk about that here in a moment. And finally, L needs to be the length of the column in feet or inches, and I'm going to point out here that this needs to ensure unit agreement. So don't forget to do your unit analysis. I'm going to move on into defining our material properties. We're going to use A36 steel as stated in the problem. The values of the different material properties I'm going to get out of table F2 in the Craig textbook, so make sure you reference your references. And I get the yield stress is 36,000 KSI, and the modulus of elasticity is 29,000 KSI. We can go ahead and also denote what those would be in PSI. And that's about what we need for our material properties. We can also do our geometric properties. In table D1 for Craig, we see that the W16 by 15 has many different properties provided, and so far the only ones that we need at this point would be the moment of inertia. Now, because we had to denote earlier that the moment of inertia was about the buckling axis, I'm writing down both of them. IX 29.1 and IY is 9.32. And so far, I'm just still gathering information and restating our problem in a recorded way. When the system is called pin-pin, and I'm going to put that in quotes, generally, it almost always means the setup that I have shown here. What this almost always means is that you would have 1 degree of freedom at the bottom, which is our standard pin. But at the top, we would have 2 degrees of freedom. This is showing us that we can move both in the vertical and it has the ability to rotate. I would tend to call this a roller instead. The length L is 20 feet. I'm going to also write it here right away in inches because I'm pretty sure I'm going to have that for my unit analysis. And our loading is assumed to be axial only. So note, I want to make sure I state an assumption that there is no bracing against buckling in any direction anywhere along this beam. Okay, this is important because the result of this assumption is that we know it will buckle about the weak axis, and therefore we will use the smallest moment of inertia, and that determines for the weak axis, which is the smallest which is IY. This just means that we're going to use the smallest IY. And because of this, I know that I can go ahead and draw the direction of the orientation, I should say, of the W flange. It will be in this direction for a plan view, looking down on top of this particular column, and as a result there are two really small, in this drawing, hidden lines indicating where the web is located. And finally, for this same model, I'm going to go ahead and label my nodes A and B as shown. Now, because we have all of this information put together, we can now draw our free body diagram. Because this drawing so far has not been a free body diagram, I'm going to go ahead and erase it and start over so I can indicate my true free body diagram. A little bit larger than the other one. So I'll go ahead and draw it and indicate the hidden location of the web. I'm going to draw my nodes at A and B. It's a little out of proportion. We have our length, L, which we know is the 240 inches. And we can start drawing in our reactions. We have AX and AY. We have BX only because it was a roller, remember that? And our loading is in the Y direction. We're going to call that P. Now, given that we know this is an axially loaded system only, we could do our analysis and find out that in fact our AX and our BX, are in fact 0, and so we can ignore them in the future. So we're going to move on and start doing our calculations. I'm going to make sure I annotate my work well. So the critical buckling load is calculated using the Euler Buckling equation number 1. Okay, we know that that's P critical, pi squared EI over L squared. Okay, we know that we're going to use, for our I, we're going to use the weak axis IY, and we know what the modulus is, and we know what the length is. Go ahead and start putting in values for this P critical. Pi squared, 29 million pounds per square inch. My IY value was 9.32 inches to the 4th. And I have a length of 240 inches. That value will be squared, and I'm going to go ahead and do a unit analysis to make sure I have my pounds per inches squared. I have inches to the 4th, and that whole thing is over inches squared. Because of that, I know that I'm going to get pounds, only, and that's exactly what we want because P critical needs to be a load. I'm going to go ahead and call this equation 2 up here, just so I can reference it in the future. Okay, Now, what I want to make sure, nope, let's go ahead and write out what the next step is. I'll continue my work over here, and I'm going to calculate all that out. I got, oops, P critical to equal 46,311 pound force. That is my answer for the buckling load. However, was that really what I was asked to solve? The answer is no. I was asked to solve or ask the question, is buckling a concern? Well, I have to compare it as an inequality. The P critical to the load, 50,000 pounds. Since it's less than the 50,000 pounds, that means we have loaded it beyond the P critical. So the answer is yes, buckling is a concern. So make sure you always go back to the beginning of your problem statement and see, is this really the answer to the problem? And often we can check and say, okay, we've focused so much on the numbers and we finally got our number answer and we're pretty sure that it's the right number. But if we forget to check and answer the question, then we really haven't completed our job. So I'm going to summarize this in words, which is always a good habit. So the column will buckle about the weak axis, which is the y-axis, once the load reaches the value of P critical, which is 46,311 pound force. This is smaller than the intended load of 50,000 pounds, and therefore, yes, this column will buckle. And with that, we're going to go ahead and move on to the next problem.